Okay, good afternoon. So today, my hope is that we will finish talking about essentially the empirical methods that economists use to try to estimate causal effects, and then following that, we'll be able to start talking about actual research that's been done in the field of environmental economics and in health as well. So basically, like what we're going to spend most of today talking about is something that's called differences in differences estimation. And there's two reasons that we're going to focus on this. One reason is that it's pretty common, and like the technique itself is used pretty frequently in environmental economics research and in health economics research. So you'll be likely to come across it if you're looking at the research. The second reason is that I think it's like fairly accessible. So understanding sort of how it works and what the potential biases are in it, like so basically under what circumstances it will work and under what circumstances it will potentially be biased estimates. Understanding that doesn't really require like a deep statistical foundation. So you don't need to be an expert in statistics or econometrics to sort of think about whether or not a diffs and diff study is going to give you a causal effect or give you a biased estimate. So for those two reasons, we're going to sort of talk about a bunch of diff and diff studies later on as the course progresses. So that's like the motivation for why we're talking about this. But I also want to sort of make sure that the context under which we're moving to this is pretty clear. So we started out talking about linear regression. We started talking about like expectations, then conditional expectations, and then how you might estimate the conditional expectation of y given x using linear regression. And then we started talking about causal effects, and we talked about how just because there's a correlation between two variables doesn't mean that one has a causal effect on the other. But I discussed sort of two cases in which you would be able to interpret the estimate that you got out of regression as being a causal effect. So one case is the case in which you're doing a regression of y on x. So it looks like yi is equal to beta naught plus beta 1 xi plus ei, where ei are these other unobserved determinants of y that might or might not be correlated with x. So one case in which your regression estimate, the slope coefficient from your regression, is going to have a causal interpretation, or going to represent a causal effect, is a case in which xi is randomly assigned. So like the overlying concern here is always that the right-hand side variable xi, which we're thinking of as being like a treatment or a policy or something like that in many cases, the concern is that this treatment or this variable might be correlated with other things that determine yi. So specifically, it might be correlated with ei. And one way that we can ensure that that won't happen is by randomly assigning xi. So I gave the example of like clinical trial where you're testing the effect of the drug, and x is a variable that basically is equal to 1 if you get the drug and 0 if you're in the control group and don't get the drug. So I gave that as one example of a case in which you know that xi is not correlated with ei, or it's not correlated with any other determinants of the outcome, because xi is randomly assigned. So by the random assignment itself, you know that it's uncorrelated with other factors that might affect the outcome. So that's one case, but unfortunately we can't usually run like randomized control trials for most of the treatments that we're interested in estimating an effect for. So then we talked about multiple regression, where the idea was that instead of running this regression, y is equal to beta naught plus beta 1 xi plus ei, you would include other variables in your regression. So it might look like yi is equal to beta naught plus beta 1 x1i plus beta 2 x2i plus beta 3 x3i plus ei, let's say. And so the idea here is that if you think there are other factors that determine y and are correlated with x, those factors are implicitly appearing in ei. So if you could basically control for those factors, then you would be able to more or less like hold them constant as x1. So the idea here is that now we have a whole bunch of x's. The original x we'll call x1. That's the treatment we're actually interested in estimating an effect for. But we're concerned that it might be correlated with other factors in ei. And let's say that those other factors are x2 and x3. If we can include those factors in the regression, then we can essentially hold them constant while varying x1. And what that's going to allow us to do then is estimate the actual effect of x1 on yi while controlling for the potential effects of x2 and x3. So we basically like in this first regression, everything here in the regression is being folded into ei. But there's some factors in ei that you really want to control for because you're afraid they're correlated with that x. So now in the second regression, you include x2 and x3 in the regression, control for those factors, and take care of the omitted variables bias. The problem, though, with multiple regression is that you need to have a really good data set, right? Because you need to basically observe all of the factors or have data on all the factors you think could be affecting y that are correlated with your x. And maybe in some cases that'll be true that you have a really rich data set where so no matter, so like the idea would essentially be that like what would happen in practice is that you run your regression of y on x, and then you go and present your results in a seminar or something, right? And you'd say, well, I found this correlation between x and y, and I'm interpreting it as a causal effect, and so the effect of x on y is beta 1. And then somebody would sit there and they'd be like, oh, but have you considered this other variable x2 that I think is potentially correlated with x and also affects y that could be confounding or biasing your estimate here? And so then you have to say, well, yeah, I did consider that, and so I ran a multiple regression where I also controlled for x2. And then somebody else will say, well, I came up with another idea which is like, maybe x3 is correlated, and you're like, okay, well, also I had data on x3, so I controlled for that, and I still found the same result. And unfortunately, like, basically these stories are limited only by somebody's creativity up to the point at which they can't sort of come up with any other confounding variables. Now again, if you're in the like if you said I randomly assigned x, then basically you eliminate all of their stories ex ante, right? Because any story they come up with, like, well, what about x1? Or sorry, what about x2? You just say, well, x1 was randomly assigned, so obviously it can't be correlated with x2, therefore I don't need to include it in the regression. But if you didn't randomly assign x, then they can come up with sort of an unlimited number of stories that might explain your regression estimate, but wouldn't result in you interpreting this thing as a causal effect. So if you have some really, really rich data set with lots and lots of variables, maybe you can sort of include enough variables so that pretty much for any variable they suggest that's omitted, you can say, yeah, I actually ran a regression where I included that as control, and I still found the same result. However, in most cases, like your data set's not going to be that rich, and so you have to sort of turn to another type of research design, another way to estimate your causal effect. And so one way that people commonly use to try to estimate omitted variables bias is to find a control group that mimics the treatment group as closely as possible, but of course was not treated, and then they do a comparison between the treatment group and the control group. So the idea here is to try to sort of replicate a randomized controlled trial, but in more sort of real world settings where you just have observational data where you're not actually going and randomly assigning some people to get treated and some people not to get treated. So where you often see this method come up is when researchers are trying to estimate the effect of some policy. So let's say that we code this policy as a binary variable, x. And to make our example more concrete, let's suppose that X is an EPA, Environmental Protection Agency policy that reduces air pollution in Los Angeles. And let's say that the outcome that you're interested in is, again, daily hospitalizations. So we want to figure out whether or not this policy that's reducing air pollution is going to affect daily hospitalizations. So one way that we could potentially try to estimate that would just be to do a regression of y and x. So regress the daily hospitalizations on whether or not that pollution policy was in effect. So you basically have like daily data for Los Angeles over many, many days. And you have sort of a pre-policy period during which the policy was not in effect, and then a post-policy period during which that policy was in effect. But the problem is that there are other factors, of course, that can affect hospitalizations, and it might change at around the same time as the policy. So those factors, if they exist, would of course create some sort of omitted variables bias where you observe a change in air pollution after the policy comes in, and you attribute that to the policy, but actually it's due to these other factors that are changing sort of behind the scenes. So the multiple regression solution, as we discussed, is to control for those factors, but you might not really have data on those factors, so you can't actually control for them in multiple regression. And so the differences and differences solution instead would be to find a control group that's similar to Los Angeles in as many ways as possible, but is unaffected by the policy. So the core idea here, or the core intuition, or at least hope, is that this diffs and diffs control groups, we call it differences and differences. It's kind of long, so often you'll just hear people sort of abbreviate as diffs and diffs. But the idea, or the hope, is that this diffs and diffs control group is going to tell us how the outcome would have evolved in the treated group absent any policy intervention, right? Because that's what we really want to know. Ideally, we'd sort of be able to observe two states of the world, right? One, so we're trying to measure the effect of this policy that reduces pollution in Los Angeles on hospitalizations. And if the policy occurs, then we can see, okay, well, given that it occurred, here's what the level of hospitalizations was in Los Angeles. Here's how many hospitalizations there were after it got implemented. What we'd like to know is if it hadn't occurred, what would the counterfactual have been? How many hospitalizations would there have been? Would it have been the same number, or would it have been a lower number? In which case we'd assume, or we'd infer that there was a treatment effect. But the problem is we can't really observe two different states of the universe, right? We can either only observe the state in which the policy occurred, if it did, or if for whatever reason the policy didn't occur, then we can only observe that state. But we can't simultaneously observe how many hospitalizations there are, both if it occurs and if it doesn't occur. So it's sort of trying to construct that counterfactual that we weren't able to observe is the goal here. And the hope is that we're going to find some other control group that basically will more or less give us the counterfactual for what would have happened in Los Angeles, at least to the degree that that control group was sort of affected by the same types of forces that affected Los Angeles during that period. So the key assumption in any diffs and diffs estimate is going to be that any factors that affect YI, that affect our outcomes, in this case daily hospitalizations, and the change in the treated group also changed in the control group. So if that's true, if that assumption holds, then the change in Y for the control group is going to capture the net effect of all of the changes in these omitted variables that we ideally like to be able to control for, but don't have data on. So in our concrete air pollution example, the idea is basically as follows. So let's suppose that there's some EPA policy that takes effect in Los Angeles on January 1st, 2010. And let's say that we decide, okay, let's use San Diego as a control group for Los Angeles. So San Diego is going to be a good control group if and only if it's basically unaffected by the policy. So that part you can be sure of, right? Because you're only going to choose a control group that was actually unaffected by the policy that you're interested in estimating effective, and you can easily observe whether or not that was true. So the first criteria is, of course, it has to be unaffected by the policy. But then the second criteria, which is harder to know whether it's true or not, is that you need to assume that any factors that affect hospitalizations that changed in Los Angeles also changed by a similar amount in San Diego. So the idea here is that maybe there's something about Southern California in general that changed around 2010 and affects air pollution or affects hospitalizations. If that's true, then we're going to observe some change in hospitalizations even if that EPA policy in Los Angeles hadn't taken effect. And so we would get a biased estimate if we just did a regression of whether the policy was of hospitalizations on a variable measuring whether or not the policy was in place. But if those changes that are happening behind the scenes are also changing hospitalizations in San Diego, then we can basically use the observed change in hospitalizations in San Diego to net out the effect of these unobserved variables. So once we have this control group, what we do is we compute the difference in differences in the outcome. So just to sort of get into the algebra here, it basically works as follows. So now we're going to subscript y and x, also all of our variables, by two indices. So it's a little bit more complicated than before, but when we're talking about these differences and differences estimates, it's basically necessary because there's sort of two dimensions on which the outcome or another variable can change. One dimension is that it could be different across units or across jurisdictions in this case. So like hospitalizations, of course, will be different in Los Angeles than they are in San Diego. So there's sort of this cross-sectional variation in the outcome and also in the policy. But then also, of course, the outcome can change over time, which was basically the dimension on which it was varying before we introduced the control group, right? So even within hospitalization, or even within Los Angeles, the number of hospitalizations is varying day to day or month to month. So now we're going to have the outcome, YIT, which is equal to hospitalizations in county I in year T, or more generally in sort of time period T. And let's assume that the policy comes into effect in 2010 in Los Angeles. So we would have to basically define our index, so our index I, so that various values correspond to various counties. So just to keep it simple, we'll assume we just have two counties here. We have Los Angeles and we have San Diego. So if I is equal to 1, that's going to indicate that we're talking about an outcome or a variable that corresponds to its value in Los Angeles. And if I equals 0, then it's going to correspond to the value in San Diego. And then T is going to represent time here. So let's let T equals 0 indicate that we're looking at a value in 2009. And then T equals 1 indicate that we're looking at a value in 2010. So the way that I'm setting this up, this is actually sort of like a trivially small data set. There's actually only 4 observations here, right? There's like I equals 0, which means San Diego, and T equals 0, 2009. So it'd be like 0, 0 is like 2009 in San Diego. Then I equals 0 and T equals 1 would be 2010 in San Diego. And then 1, 0 would basically indicate you're in Los Angeles in year 2009. And then 1, 1 would indicate Los Angeles in 2010. So you actually have 4 observations in this like super compact data set. But with those 4 observations, you can basically construct the following quantities. So first you could look at the change in Los Angeles hospitalizations, which would be Y11 minus Y10. And then you could look at the change in San Diego hospitalizations, which would be Y01 minus Y00. And then you can compute this difference in differences estimate. So literally here is the difference in these two differences. And it would be the change in Los Angeles hospitalizations minus the change in San Diego hospitalizations, or as you can see here, it would be the quantity Y11 minus Y10 minus the quantity Y01 minus Y00. So the intuition here is that, and this is going to be based on your assumptions, so it isn't guaranteed to hold, and you have to think carefully about whether or not it does hold. But the idea here is that any omitted variable, or the hope is that any omitted variable that changes hospitalizations in Los Angeles is also going to change hospitalizations in San Diego by a similar amount. And so the change in the San Diego hospitalizations is basically capturing what the omitted variables bias really is here. And you're subtracting out that omitted variables bias because you're subtracting out the change in San Diego hospitalizations. And what you're left with is hopefully just the causal effect of the policy on Los Angeles hospitalizations. So diffs and diffs is going to work under sort of a very specific set of assumptions, and it's very important to recognize and understand what those assumptions are. Basically, what types of biases it can remove and what types of biases it's still going to be vulnerable to. So one of the things that it can do is it can net out any factor that changes by an equal amount across both the treated and the control groups. So let's suppose that there's some omitted variable called ZIT that affects your outcome hospitalizations, which is YIT, right? So just to give you some example, ZIT could be like the average temperature in the two counties, right? Because we talked about how temperature is correlated with pollution levels, and temperature also has an independent effect on hospitalizations, and so it's something that you want to control for. Now, temperature is sort of an easy case in the sense that in most data sets you'd actually be able to construct a temperature measure because it's well measured by the National Weather Service. But just imagine that for whatever reason you didn't have data on that, so you couldn't control for temperature. So let's write the causal effect of ZIT on YIT as being alpha. So there's some alpha is not equal to 0. If you change ZIT, it has some effect on hospitalizations. If there's a change in temperature, it has some effect on hospitalizations. And let's further assume that this variable changes by delta units for both Los Angeles and for San Diego. So the effect of the change in ZIT on the change in Los Angeles hospitalizations is going to be equal to delta times alpha. Because what you have here is the change in Los Angeles hospitalizations. And so to the degree that temperature is changing by delta units and it has an effect alpha on and changing temperature by 1 unit affects hospitalizations by alpha, then the product of those two things is going to give you how much of the change in hospitalizations is due to this change in temperature. And so ideally what you'd like to do is be able to net out that effect of the change in temperature from your observed change in Los Angeles hospitalizations. But if you don't have data on temperature, then of course you can't do that. So what we're going to hope then is that the change in San Diego hospitalizations is also affected by temperature, and that the change in temperature in both Los Angeles and San Diego is the same, right? So that was this assumption right up here. Suppose that ZIT changes by delta units in both Los Angeles and in San Diego. So if it's changing by delta units in San Diego, then we know that again the effect of the change in temperature on San Diego hospitalizations is going to be delta times alpha. And then if we do the diffs and diffs, so we do the change in Los Angeles minus the change in San Diego, to the degree that the only thing that's changing San Diego hospitalizations is this change in temperature because there's no policy change. So to the degree that's true, then we're going to get basically delta alpha for the change in Los Angeles hospitalizations. We'll get delta alpha for the change in San Diego hospitalizations, and those two things will net out to be 0. And so that's actually desirable because what we want to do is basically eliminate the effect of that factor from the observed change in Los Angeles hospitalizations. And so if this omitted variable ZIT is changing changing equally for both treated and control groups, then it's not going to bias the diffs and diffs estimated. Now, of course, temperature is going to be the only thing that's changing behind the scenes here that might be having an effect on hospitalizations. But you could tell the same story for any other variable as long as you're willing to assume that that variable is changing by the same amount in both Los Angeles and in San Diego. So you could have 10 of these ZITs, and they could all have different effects: delta 1, delta 2, delta 3, and so forth, and delta 10. And you could go through the same exercise and have basically the change in San Diego hospitalizations being equal to the sum of all of those, like delta 1 times ZI or Z1, actually delta 1 times delta 1 times alpha 1, and then delta 2 times alpha 2. Sorry, so the effect for any variable Z1T, Z2T, and so forth, or Z1IT, Z2T, so forth, would be like delta 1 and delta 2, and so forth. And then so that would be the change in the units for each of those variables, and the effect would be like alpha 1, alpha 2, and so forth. And you end up with like the sum of like delta 1 times alpha 1 plus delta 2 times alpha 2, and so forth. But as long as that sum is the same in both San Diego and Los Angeles, so as long as those factors are changing by the same amount in both counties, then you're going to end up netting out the bias that's due to them. So one thing that diffs and diffs is able to do is that it can net out the bias from any factor that changes by the same amount in either or in both counties. The other thing that it can do is that it can net out any factors that differ across the treated and control groups, but are constant over time. So let's sort of now switch the story here and think about a potentially different type of omitted variable bias. So let's suppose there's some omitted variable ZIT whose causal effect on YIT is again alpha. But let's further suppose now that ZIT is different for Los Angeles and for San Diego, but that it doesn't change over time. So basically ZIT is equal to Z star in Los Angeles in both years, and ZIT is equal to Z star star in San Diego for both years. So now ZIT might be, for example, the effect of, say, traffic, right? So traffic is obviously something that affects air pollution because when there's more cars on the road and when they're congested, they're going to generate more emissions, so air pollution is going to go up. And furthermore, you can think that traffic might have some effect on hospitalizations through a variety of factors. On the one hand, if people are stuck in traffic, they might sort of get stressed out, and maybe that would cause them to have a heart attack or something like that. Who knows? On the other hand, it could have a direct effect in terms of accidents, although that would be somewhat easier to control for in the data because you'd probably be able to sort of parse out what was like a respiratory admission versus what was an admission because you got into a car accident. But you can tell a variety of stories under which traffic might have some effect on hospitalizations, even independent of its effect on air pollution. And we know that traffic in Los Angeles is really bad. It's worse than San Diego, and furthermore, it's always bad, right? So it's not just that like it's bad in 2010 or it's bad in 2009. It's just perpetually bad. So let's suppose that traffic was really bad in Los Angeles in both years, and then only somewhat bad in San Diego in both years. So the effect of this omitted variable traffic on the change in Los Angeles hospitalizations is now going to be the following. So in Y11, so for outcome, for hospitalizations in Los Angeles in year 2010, it's going to be equal to alpha times Z star, which is the level of traffic in Los Angeles. And then for Y10, so that's Los Angeles in year 2009, it's going to again be equal to alpha times Z star because the traffic was the same in 2009, we're assuming, as it was in 2010. So the overall effect of traffic on Los Angeles hospitalizations, once you take this difference, is going to be 0, right? Because basically its effect in 2009 is netted out from its effect in 2010, and you end up with it having no effect at all. I mean, it has an effect, but it has no effect on the change in hospitalizations. Likewise, in San Diego, it's sort of the same story, but now it's alpha times Z star star instead of being alpha times Z star. But again, since traffic is the same in San Diego in both 2009 and in 2010, it's contributing the same to both of these quantities, both Y01 and Y00. And so it again nets out when you take the difference between the 2010 outcome for San Diego and the 2009 outcome for San Diego. So it's still going to be contributing nothing to the change in